oben. Today in this webinar, I will talk about the different methods of native page. First of all, I want to give you an overview of the structural differences of native and denatured proteins. Then I will switch to the separation of native proteins with a Tris-Glycine buffer system. And then I will show you a very special kind of native page, the blue and the clear native, which are for separation of membrane proteins and hydrophobic protein complexes. And at the end, I will show you the 2D Blue Native SDS page, which is a combination of native and denaturing electrophoresis. First of all, the structural differences of native and denatured proteins. So, native proteins do have a secondary structure, which is influenced by interactions within the amino acid sequence, for example, hydrogen or disulfide bonds. As a secondary structure, alpha helix, the beta sheet, and the beta loop are described. Then tertiary structure is developed. It's the three-dimensional active protein conformation. And also for different proteins, a so-called quaternary structure is developed. It's a multimer of protein molecules which are formed by disulfide bonds between the protein monomers. The denaturing process with SDS and reducing agents like DTT or beta-mercaptoethanol leads to the disruption of the disulfide bonds, and protein structure is some kind of stretched with a SDS. And this leads to destroying of the secondary, tertiary, and quaternary structure. If you use SDS treatment but no non-reducing reagents, the disulfide bonds remain intact. Only a slight denaturing is achieved. And here's a special kind of denaturing. The SDS treatment and the reducing agents are the same, but the reduced disulfide bonds and the sulfitryl groups are alkylated, and this prevents further oxidation and reformation of the disulfide bonds. Now, this is what happens when proteins are denatured. Now we will talk about the separation of native proteins in their globular intact native structure. They can be separated in different buffer systems. Here I will describe the separation in the Tris-Glycine buffer system. So this is a buffer system similar to the Lemley, but in the absence of SDS and reducing agents. So all Serva TG prime precast shells can be used for this application because the gel matrix does not contain any SDS. So for this more common but very simple kind of native electrophoresis, these gels can be used. This is an example of a Serva TG prime gel. It's a gradient gel, 4 to 20% acrylamide, and here are some markers and proteins separated. The first two lanes show our IEF marker. This marker is optimized for separation in IEF and contains servalide. That's the reason why it looks a little bit different to the other lanes. So the Serva light, which is a carrier ampelite, interferes with the electrophoresis settings, so the separation is not really good. The lanes 3, 4, 5 show our protein test mixture number 6. And here you can see clearly separated bands. But nonetheless, this marker is a special SDS page marker, and here it is separated under native conditions. The band in the middle is the BSA at 67 kDa, and in the two lanes on the right of the test mixture, you see here the BSA band. So this is the 67 kDa band, and in lane 8 and 10 again the test mixture is applied on the gel. In lane 9, where it looks like an empty lane, the insulin with 6 kDa was applied, but it was not detectable in this gel because it migrated out of the gel. So it behaves completely different under native conditions than in denaturing gels, because using this kind of gradient under denaturing conditions in SDS page, the insulin is easily detectable. So the Blue Native and the Clear Native page are special applications to separate membrane protein complexes, membrane proteins, and hydrophobic protein complexes. So this is a little bit of a different method than the method shown before, because the limitations due to PI value, isoelectric point, and these things are not as big in this method as in the method described before. So it's a method, as I already told you, for separation of membrane proteins or protein complexes. These are extracted with the help of mild detergents such as Triton, dicotonine, or dodecyl beta-D-maltoside. All these detergents can be used for extraction. They can also be used as a mixture. So the extraction procedure has to be optimized for each sample. So therefore, we offer a so-called detergent sampler, which contains each detergent. So the customer is able to optimize the protocol for extraction for the special sample or the special protein he's looking for. So the Blue Native page is performed with a special buffer system. The cathodic buffer contains Comasi Brilliant Blue, or the equivalent Serva Blue G, and the anodic buffer do not contain any dye. So what's the reason for this special buffer system? The anionic dye, the Comasi, acts like the detergent SDS, but without denaturing the protein, so the protein-protein interactions are not disturbed. But the proteins get an overall negative net charge. And due to this net charge, the band sharpness is very high in this separation, because each complex which forms a separate band has a negative net charge, and therefore the bands get sharper because they have all the same charge. Furthermore, the negatively charged proteins migrate from cathode to anode, and there are no restrictions due to PI values. So some proteins who will have who will be uncharged in this buffer system will also migrate from cathode to anode because of the di-protein complex. Here's an example of a separation of plant proteins on a precast Serva gel native gel. So the proteins or the protein complexes separated here are from plants and are connected to the chlorophyll complex. And during the electrophoresis, so after 1/2 or 2/3 of the run, the blue cathode buffer is replaced by a colorless cathode buffer. The reason why this is extremely useful, I will give you later on, because plotting is also an issue. This is an example of protein separation on 3 to 12% native gel. So here some of our marker proteins are separated, but not all proteins will migrate according to their molecular weight. One example for this is the carboanhydrase, because it has a molecular weight of 29 kDa, but it migrates at much higher molecular weight compared to the trypsin inhibitor, which is nearly at the bottom of the gel. The carboanhydrase is right in the middle. So not all proteins will migrate very well in the gel and can be used as marker proteins. This depends on their on the influence the chromacy has on the protein and the ability of the protein to form complexes with a chromacy or not. This is an example of a 4 to 16% gel. Here there are also applied some of our marker proteins, and the gel is subsequently stained with Serva Blue Air. So this is now the point to explain why it could be important to change the buffer, the blue stained cathode buffer, to the unstained cathode buffer, because during electrophoresis the chromacy migrates into the gel, and if the buffer is not replaced, this chromacy in the gel will inhibit plotting or protein transfer when a subsequent electroplotting is performed. So that's the reason why the cathode buffer is replaced to the unstained cathode buffer, and then the proteins can be transferred according to a standard procedure for semi-triplotting, for example. But you always have to keep in mind that native proteins may show different reactivity towards the antibodies used, because many antibodies do not react with native proteins because folding of the proteins may cover the epitope the antibody reacts with or may react with, and so this can be a problem in subsequent Western blot detection. The other special form is the clear native page. So why should one perform a clear native page? So this is the method of choice if the subsequent analysis is dye sensitive, for example, enzyme activity assays. In this special kind of electrophoresis, the net charge of the protein is pH dependent, and so this determines the migration in the electric field. This means that the separation of proteins with pI lower than 7 at physiological pH is possible. If the pI is higher, these proteins could not be separated in the shell. A special application, or an application which gives further information about the protein complexes, is the combination of the native electrophoresis with the denaturing electrophoresis. So it is the so-called 2D Blue Native SDS PAGE. What happens there, and why is it a good thing to combine both? In the first dimension, there's a separation of protein complexes, and in the second dimension, there's a separation of the subunits of these complexes. So you will get further information about the components which form the protein complexes. And to find out whether there are the same subunits in different protein complexes, you may perform Western blot analysis of the second dimension, which gives you more specific information about these smaller proteins. So it's a very convenient method to analyze very hydrophobic proteins, and it allows functional proteomics and the analysis of complexes and supercomplexes. So after the first dimension in this kind of electrophoresis, no staining of the gel is necessary because the anionic dye is still bound to the proteins. Then the vertical lane of interest is cut out of the Blue Native gel. It is equilibrated in SDS buffer and then transferred to the SDS PAGE gel for the second dimension. During the second dimension, the protein complexes dissociate into single proteins, and also the protein dye complexes dissociate. So the dye, the Comassi blue, will migrate in the running front. After the second dimension, there are different detection possibilities: gel plotting and Western blot analysis, or direct protein staining and documentation analysis of the gel. This is an example for the first dimension of the 2D Blue Native PAGE. The lane 1 shows separation of membrane complexes by clear native PAGE. Lane 2 shows the separation by Blue Native PAGE. And due to the different running buffer systems and the absence of Comassi in the clear native PAGE, shows a different pattern than in the Blue Native PAGE. This is the second dimension. So after the native PAGE, the gel strip from the Blue Native PAGE is subjected to SDS PAGE, and it gives a characteristic pattern. So make sure that this spot or this subunit is the same as the subunit here. Further Western blot analysis with specific antibodies may be performed. Another type of native PAGE is the isoelectric focusing. This is a really special kind of native PAGE because in this application, proteins are not separated according to their molecular weight, but according to their isoelectric point. The isoelectric point is pH dependent, and at this pH the protein do not have any net charge, so it won't migrate in the electric field. This means that when reaching this point, nothing happens anymore in this kind of electrophoresis. So this is an example of vertical IF gel. So there are some marker proteins separated, and this is an IF gel with a gradient 3 to 10. But in the vertical system, due to the buffer system and all these things, it's not possible to see or to detect the proteins with pI above 8.3, because these proteins won't migrate in the gel because they do not have the right charge or they are uncharged. This is an example of a horizontal IF gel. In this application, film-backed gel is used, and this is a separation of for MS diagnostics, so it's used for multiple sclerosis diagnostics, and it's a really special application. But it looks a little bit different than vertical gel, because this is a real endpoint method, and the gels are very thin. And for plotting, it's very important to remove the plastic film at the back of the gel to ensure current flow. And for this reason, we also recommend press plotting protocol to transfer these proteins onto a plotting membrane for further analysis. So I hope everything was helpful for you. And if there are any further questions, please ask.